the importance of that formula, the B equals P times 10. Well, I remembered how to find the next number that's going to end in 1 that has 17. You got to times 17 by 3, 51. Because you want all the numbers to end in 1. 91 times 11, 1011. 1001 times 51, 51,000. But then when you take the time to write it out, because 51,051 is divided by 17, 13, 11, 7, and 3. That number is divisible by 3, so you can just count out 1, 2, 3 divisible by 3, 1, 2, 3 divisible by 3, and keep it up, and then you can start back and go to sevens. There's 1, and then go back and start at 11, going up the number line or down the number line. I accidentally put 49 when I meant to put 50s, but it works the same either way. And for example, let's take 5981 divided by 7 is 749. 2 14 8 56 and 3. So that comes out to 7,283. But the importance of with this, we know where we can basically drop numbers and start knowing what numbers are divisible by what when we put it into a computer program. And if we want to jump 51, adding 19, then we got to do 19 times 9, because the soonest a 9 can turn into a 1 is a multiple of 9, so it comes out to 180, 171, because it'd be 8 plus 90, 171, and then 51 times 171, and that'd be where 19 gets added into the mix. But this shows us where 17s and 13s and whatnot are at, but we want to know 19, which times 9 equals 171, but we want to jump 171 up the number line to where it needs to be, so it's 171 times 10 equals 1,710 plus 171, and that'd be 1,881, but that is nowhere close to 51,000, so what we need to do is take that 171 times 30, I believe. Equals 171,000 times 3,0,0,3,2 plus 171. Well, I mean, in this case, we'd be jumping the gun a little, so we could subtract. So it would be 9, 2, 1, 1, 5. Oh shit. Well, never mind, because we want it to end in a 1, so we are going to add, which would be 5, 1, 4, 71. 50, 1,000. So the nearest one would be 200 above that, and that would be divisible by 19. That should be divisible by 19. I'm going to have to get out my calculator for a big number like that. One, 4, 7, 1. Yeah, divisible by 19, so it's 2,700. So 51,471. $1,471 minus 190 is 5281. So that's 60 past there. Minus 380 is 5901. So that number that's divisible by 3 right there should also be divisible by 19. Yep, 2,679. So, and now that we know that's divisible by 19, we'd just be able to count every 19, but that's what I'm talking about, where a computer program could do this faster. So essentially, as long as we know where we want to go, we can go to jump in the number line wherever we want with any numbers. And then but the reason for the gap of 6 at 17 is because mathematicians have proven that there's a gap of 16 always. So 51 0.051 times 10 equals 51 0 51 0, and then plus 51 0 51 is 165 165 165 So 51 0 51 6 5 6 1 plus 5 10 10 is 1 7 0 2 7 0 1 million 72 0 71 plus 0 1 5 0 1 5 1 8 5 2 8 5 1 1 5 8 2 5 8 1 Okay. These numbers here are where there will, because any number that's divisible by this, which all these are, means that this pattern will pop up where 51, this pattern before and after pops up. So that means it happens here, 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 and here. And as you can see, I can just keep jumping and checking all those spots. But what that matters is, as we look closer into the patterns that keep happening, like how right here is a number divisible by 19. So 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. That number should be divisible by 19, which I can do. 51, 51, 0. 91, 19. Yep, it is. And but it just means we can narrow out faster what is prime and what isn't prime, because instead of just guessing or sitting there running everything through, it would be pointless to run 81 or 51,081, 51,111. It'd be pointless to run those through any tests or anything, and we can jump these numbers because that's times 10. We can change that 10 into 100, 1,000, 10,000, and then add 51, and then boom, all those numbers, all that pattern will start again no matter how many zeros we stack on. So essentially, if we write a computer program to do it, we can jump these numbers up anywhere and just start taking out any numbers that aren't primes. And if you want 51,051 times 171, yes? No.
What's happening, Gracie? You want to go outside, kid? Daddy let you
It'll
outside.
become
Somebody will do it.
8,700.
Kind of trouble I get in here outside, eh?
9, 7, 2, 1. And if we want to do it with 23, we have to do 23 times 7 equals 181. Because that's 161. And you can keep jumping the number to where whenever you get to these higher numbers, it starts doing it with 3s, 7s, 6s, 9, and as you keep adding primes into it, you can start off at bigger numbers. And then something like this just times 101. It'd add all the primes that go up into it plus the prime 101. This would be almost like 10 factorial, except this factorial uses primes only. And maybe this can help us narrow down the twin prime conjecture. I'm not entirely sure if it will or not, but I definitely have to do some more study and work into it. If anyone who'd listen, I appreciate anyone that's listened.